Hello everyone from Math 2200, Discrete Mathematics. It's Professor Wenson here again with a video on your Zybooks, section 13.3, titled Graph Isomorphism. Okay, isomorphism, if you break it up, is iso meaning equal or same, and morph meaning form or structure. So this section is all about determining if two graphs are isomorphic, meaning they have the same structure. There's more to the meaning, of course. We'll get to the definition in a minute. Alright, so consider the two graphs pictured here. And you see they look basically the same, right? They have the same they're basically the same drawing. Right? They look very similar, but they're not quite the same graph. Right? Based on previous sections, section 13.2 and 13.1, we would not call these graphs the same because they have different, vertices, different labelings for the vertices, right? The left graph has vertex set A, B, C, D, E, F, whereas the right graph has vertex set, 1, 2, 3, 4, 5, 6. So they're very similar because you see they have the same structure. But again, they're not called equal graphs or the same graph because of the different labelings of the vertices. Now I could easily relabel 1, 2, 3, 4, 5, 6 as A, B, C, D, E, F going clockwise, and then they'd be the exact same graph. And that's what it means to be, for two graphs to be isomorphic. Basically, if you have two graphs and you say they're isomorphic, that just means you could relabel the vertices of one graph with the labelings from the other graph and get the exact same graphs, the same vertex set and the same edge set. And we'll see all that coming up. So of course, when the two graphs are drawn as they are, right, with the same drawing, it is easy to verify that the structure of the graphs is the same. It's much more difficult to determine that the graphs have the same structure when given, say, the adjacency list representation. Remember these adjacency lists from section 13.2. So here are the adjacency lists for these two graphs up here. But again, if you kind of follow, if you draw these, if you write the adjacency list in the same way, where you do alphabetical order, or do numerical order, least to greatest. Look at where all the A's are. There's A here, here, and here. Match that up to where all the ones are over here. You see ones here in the same place as this A. This one is in the same place as that A. These ones are in the same place as these A's. And there aren't any ones over here that don't correspond to an A over here. So if I relabeled 1 with A, or if I relabeled A with 1, so things would be working out structure-wise. And then I could do the same thing for B, C. Look where all the B's are. There's a B here and a 2 here. And there's B's here and here, 2's corresponding. B here, B2 here. And that's it, right? Where every B is in this adjacency list, there is a 2 in this adjacency list. And there aren't any 2's over here where there are B's over here, right? Where there aren't B's over here. So the 2's and B's correspond. So I could map, replace B with 2, or you could say map B to 2. And I could do the same with C and 3, D and 4, E and 5, F and 6. And if you can do that with every single vertex, if you could just switch the vertices and get the same graph, then those graphs are called isomorphic. All right. So the drawings of the two graphs, right, reveal a correspondence between the two sets of vertices that make it easy to verify that every edge in the graph on the left corresponds to an edge in the graph on the right, and vice versa. Right, so the edge AB would correspond to the edge 1, 2, and vice versa. Every edge on the right graph corresponds to an edge on the left graph. The edge 2, 3 would correspond to the edge BC. So here, finally to the definition of isomorphic graphs. Two graphs are said to be isomorphic if there is a correspondence between the vertex sets of each graph such that there is an edge between two vertices. If there is an edge between two vertices of one graph, if and only if there is an edge between the same, the corresponding vertices of that other graph. The graphs are not identical, right? Because again, the vertices are labeled differently, but the vertices could be relabeled so that they are identical. Right? So if you can do that, then the graphs are said to be isomorphic. All right, so a more formal definition here involving vertex set and edge set. So what does it mean for graphs to be isomorphic? All right, so let G be a graph with a vertex set V and an edge set E, and say G prime is a graph with a vertex set V prime and edge set E prime. All right, so G and G prime are isomorphic if there is a bijection, say called, now remember a bijection is a function that's both one-to-one and onto, right? A one-to-one correspondence. So if you can find a bijection from the vertex set of G to the vertex set of G prime, such that for every pair of vertices in V, that edge is in the edge set of G if and only if their corresponding vertices form an edge in the edge set of G prime. All right, and then this function, this bijection that you create that makes this happen, the function f is called an isomorphism from the graph G to the graph G prime. All right, so again, lots of fancy stuff going on here. But, they give us an example down here. All right, so I'm actually going to draw this out, right? And I'll establish this isomorphism, show these graphs are isomorphic on a piece of paper. All right, so here are the two graphs we were given before the animation in that activity. So I've got this black graph, called G1 with a vertex set, V1, and I'll write out the vertex set here, right? It's got vertices A, B, C, D, and E. And edge set, E1. And, I'll write the edges up. So we got edge AB, got edge AD, edge BA I don't need to do, BC, edge BD, and then C, no CD, CE and DE. Right. Okay, so there's edge set E1 and vertex set V1, and I'll do the same thing for G2. It has a vertex set V2 with vertices labeled 1 through 4 here. Or sorry, 1 through 5. There should be the same number of vertices, right? Two graphs with different numbers of vertices aren't going to ever be isomorphic. And then edge set, E2, and all this in red. Let's start with 1 here. We got 1 to 2, 1 to 5, and 2 to 1 I got, 2 to 3, 3 to 2 I have, 3 to 4, 3 to 5. And finally 4 to 5. Okay, so there's now the edge set. Now notice if they're going to be isomorphic at all, right? They may not be. Now this first example they are, but if they're going to be isomorphic, they better have the same number of vertices and the same number of edges. Notice that both of these have 6 edges. Because in isomorphic graphs, right, every edge over here has got to correspond to an edge over here, and vice versa, right? Got to go backwards. So they better have the same number of edges. So that's an obvious, way to tell if they're not isomorphic, right? If I threw another edge in here, say from 1 to 3, then all of a sudden they'd have no chance of being isomorphic. Okay. So now let's try to determine, how can I create a mapping? Can I create a function that basically relabels A, B, C, and D as 1, 2, 3, 4, and 5 and gives me the same edge set, as for the red graph? All right. Well, let's see. One thing I could do is let me look at, now I know they said this would be difficult to look at, but I'm going to look at the adjacency lists. Alright, I'm going to look at the adjacency lists for these graphs and make some comparisons. So for a graph, G1 here, again, vertex A, B, C, D, and E. And A is, I'm going to put them in alphabetical order. A is adjacent to, just B and D. B is adjacent to A, C, and D. C is adjacent to B and E. D is adjacent to A, B, and E. And finally, E is adjacent to C and D. Okay, now I'll do the same for graph, G2. We had vertices 1, 2, 3, 4, and 5. 1 is adjacent to 2, and I'll go in numerical order here, lowest to highest. 2 and 5. Right, 2 and 5. 2 is adjacent to 1 and 3. 3 is adjacent to 2, 4, and 5. 4 is adjacent to 3 and 5. And 5 is adjacent to 1, 3, and 4. Alright. Then I'm going to try to rearrange these so they look, basically, is there a way to rearrange these adjacency lists so they have the same structure? And then that'll help me with my mapping. So, all these vertices that are adjacent to 2 other vertices, in an isomorphism, remember the structure is going to stay the same. So any vertex in this graph that's adjacent to 2 vertices would have to correspond to some vertex in this graph that is also only adjacent to 2 vertices. All right, hopefully that makes sense, right? Because I can't have B correspond to 1. I can't map B to 1 because B has 3 edges coming off of it. So it should correspond to 3 edges in the other graph if they're isomorphic, but 1 only has 2 edges coming off of it. All right, so there'd be this edge from B to D that wouldn't correspond to anything over here. All right, so so again, I'm going to do some shifting around. Now, I think the easier ones to match up would be the 2 and the 5 with the B and the D. So either B has to go to, you see the 3 vertex and the 5 vertex over here have, adjacent to 3 other vertices, and the B vertex and the D vertex over here also, to 3 vertices. All right. So let's see. Well, let's see. In B and D, there's ACD, ABE. So they both are adjacent to A. So they share an adjacency with A. Now 3 and 5 have 2, 4, 5, 1, 3, 4. So you see how they're both adjacent to 4, and B and D are both adjacent to A, and those are the only ones that they share in common. So it's kind of like code breaking, right? What vertex over here represents what vertex over here, and can I match them up? So it looks like based on those two rows of this list, I need to have. So I'm going to create a function. I'm going to start creating a function which should be a bijection, right? It should be both 1 to 1 and onto. I'm going to create a function again. Let's say I'll call it f from vertex set for graph 1 to the vertex set for graph 2, and we'll do the following here. Now I'll just create a mapping, all right? So again, we have vertex set 1, and then vertex set 2 is the target. So just based on these 2 rows of these adjacency lists, it looks like I'd have to map A to 4. I have to map A to 4, or relabel A as 4. All right. So let me do that. All right. So now, continuing on. So now A is 4. And maybe I'll write that here, and 4 maps to B and D. All right. 3 and 5. And I'm seeing B and D in these 2 rows. So either B goes to 3. So again, this is now, A. Think of A as 4 and 4 as A now. So 3 and 5 have to be either B or D. So B could be 3 or 5. D could be 3 or 5. But then looking back here, that's a lot of logic. All right. Again, kind of like code breaking. But if you look back at my row D, the 3 adjacencies, B and D, or 3 and 5 here. If say I were to let B be 3, right, let's test one. If B was 3, so if these were the same, all right, if B was 3, well, you got B to A, then 3 to 4, right? Then 3 to 5. Now remember, if B is 3 and D is 5, great. D would have to be 5 in that case. Now, what if I switched them? What if I had B be 5 and D be 3? Well, let's see. 5 to 3. Those work out too. But then you've got E there. All right. Okay, so actually this is hard to keep track of. They even mentioned earlier adjacency lists probably aren't the best way to do this, but I wanna hammer it home. All right, let's do this. So what? All right, so if let's do some cases here. So again, A has to be 4. We've seen that. A has to be 4 based on these here. So again, if A is 4, then B or D have to be 3 or 5. So what if I did this? What if B went to 3 and D went to 5? Let's see if this will give me. And then again, A has to be 4. That's a given. Now if this were the case, if B went to 3 and D went to 5, then I would say this is B. over here, B slash 3 goes to 2, 4, 5, goes to 2, which I don't know the letter for yet, goes to 4, which is A, and goes to 5, which I'm saying is D in this case. Again, this is a big if. Then 2, let's see again, B here is 3, A is 4, D is 5, so 2 would have to be C in this case. 2 would have to map to C. Now let's see if this runs me into any problems. Now if 2 maps to C, so this is 2 and C are the same. And 3 to B, E would have to go to 1. Right, with the BE line and the 2 line. E would have to go to 1. And let's see if E goes to 1. You got C is 2, 2, D is 5, 5. It looks like that does it. All right. So my first choice of B and D worked out. And let me show you. All right, let me show you. So now I'll do these mappings. So again, I had A going to 4, B mapping to 3, D mapping to 5, C mapping to 2, and E mapping to 1. And do you see there's a 1-to-1 correspondence here. All right, there's a 1-to-1 correspondence. And now let me just reorder these adjacency lists in this fashion. All right. So watch, right? Watch. I can reorder the adjacency lists if I have these mappings. So let's do this. So I'll just make the replacements over here. So 1 I said was E. So say I relabeled these all A, B, C, and D, and E. And then 2 was C, and 5 was D. So C, D. And you see how now this first row here corresponds exactly to this row here, right? And then 2 I said was now C, and that maps to 1 and 3. 1 is E, 3 is B, so I'll put them in order, B and E, right? So in this row here corresponds exactly to this row here. Beautiful. And then 3, 3 I said was B now. And then 2, 4, 5. 2, 4, 5 is C, A, D, or A, C, D if I put them in the alphabetical order. And do you see how this row here now corresponds to this row here exactly? And 4 is again A. 3 and 5 are B and D. So this row here corresponds exactly to this row here. And then finally, the 5 I said was mapped to D. And then 1, 3, 4 are E, B, and A, or A, B, E if I put them in the alphabetical order. And now this row here corresponds exactly to this row here. Now, so there is a 1-to-1 correspondence between the vertex sets that also gives me a 1-to-1 correspondence between the adjacency lists. All right. There's this went to this. These are the same. Again, A went to 4. These rows are the same now. Have the same structure, same adjacencies. When I relabel, B went to 3. C went to 2. This row to that row, and D went to 5. Right. So the 1-to-1 correspondence here, shows me that these have the same. They have the same structure. You could also even just match up the edge lists. All right. I could rearrange these, just do the same, do this mapping to the edge list, and show you that they're the same thing. All right. So like here was edge list 1, and then if I just rewrite edge list 2 down here, you can see edge list 2 coming up when I do this mapping. See, the edge AB would go to, would correspond to edge 4, 4, 3, or 3, 4. Right, I'll just do 3, 4. That would, AB would correspond to 3, 4. AD, A went to 4, D went to 5. So this corresponds to the edge 4, 5. AD. BC, with this mapping, 3, 2, so corresponds to the edge 2, 3. 3, 2, same thing. Then BD, B went to 3, D went to 5, so this the edge BD corresponds to the edge 3, 5. CE, C went to 2, E went to 1, so CE corresponds to the edge 1, 2, and DE 5, 1 corresponds to the edge 1, 5. And let's see if every edge is actually accounted for. 3, 4, great, 3, 4. 4, 5, 4, 5. 2, 3, 2, 3. 3, 5, 3, 5. 1, 2, 1, 2. 1, 5, 1, 5. Exactly the same. So this bijection, this function between the vertex x, this relabeling, shows me that these, gives me the exact same edges, right? Tells me what edges correspond to one another. And these graphs actually do have the exact same structure, right? So after all that, right, I would definitely say that these two graphs are isomorphic. Again, very easily, just if I were to relabel, right? If I were to relabel, I'll do it one more time. If I were to relabel the 1 as E, if I were to relabel the 2 as a C, if I were to relabel the 3 as a B, relabel the 4 as A, and relabel the 5 as D, then everything matches up. The vertex sets are now the same, A, B, C, D, E, and the edge sets would be exactly the same. All right. So yeah, so you can see, especially with the adjacency lists, it can be a bit tricky. You might want to just look at the graphs. Maybe it would have been easier to see. If I just move this edge E over here, watch. If I just moved E over here, say I move this over here, there's E, and then you'd have this E to C, just replaced over here, and then E to D over here. And you see the cycle, right? You see this, I'll put this green graph in here, with the B to D across. That's kind of like this cycle here with the B to D across. So B and D would have to be the 3 or the 5, and then you can cycle around, right? Where maybe again E, or and then you have the triangle down here, 3, 4, 5 triangle. So the ABD triangle has to correspond to the 3, 4, 5 triangle. Shapes will stay the same too. Triangles or 3 cycles in one graph will go to a 3 cycle in the other graph. 4-sided shapes in one graph, if it's isomorphic, will go to 4-sided shapes in the other. Okay, so this again, the structure is preserved. Everything should be the same with this relabeling, this bijection. All right, lots of ways to look at it. All right, and then you can watch the animation. They're showing you how the edge sets match up with this labeling, all right, with this relabeling, this function, and yeah, show that these are isomorphic. All right. Now, if you can't find this, right, there are going to be some function. There are going to be pairs of graphs with the same number of vertices, the same number of edges that are not isomorphic. There's no way to find a bijection that does this. All right, so those are a bit trickier to see. All right, as if this wasn't tricky enough. Okay. So here's another example. The diagram below shows two graphs. We can determine, we'll try to determine, if these are isomorphic. Right? Are these isomorphic? Now again, I can really see how they are. All right, let me show you. I'm gonna do a little, maybe an easier version of what I just did. I'll graph these on paper and then show you with a little motion, just moving one vertex around, how we can see that these are, well, we can see pretty clearly if they're isomorphic or not. All right, I'll draw this up on paper and we'll take a look. So here are these two graphs that they're in this next activity. And again, we're trying to determine if they are isomorphic. I mean, again, they have the same number of vertices, the same number of edges, right? They both have 5 edges and 4 vertices. But is there a way I can I relabel these 1, 2, 3, and 4 and get the same edges as I got over here? Or, vice versa, if I make that relabel, could I relabel these edges, vertices as A, B, C, D in some way and get the same connections, right? The same exact edges. All right, so now you could do the whole adjacency list thing that I did earlier. Maybe even just look at the graphs and see what edge over here corresponds to what edge over there. I think it'd be easier to maybe, again, the more vertices and edges there are, the crazier it gets, the harder it gets to determine if there's an isomorphism, obviously. But what if I were to move this vertex B over here and make the same connections? So watch what happens when I do that. So I'm going to move B over here and keep, D, A, and C like this. So D, and then A is to the lower to the right of it, and C is lower left. So all I did was move vertex B on the other side of DC here. And let's make the same connections. All right, so we have D to A, we have D to B, right, so D to B. We have D to C. Okay. We have A to D, A to C, and then nothing else. B to D, B to C, nothing else, and then C to B, got it, C to A, got it, C to D, got it. All right. Can you see the similarity now? Just moving the one vertex somewhere else and making the same connections, the same edges. Now really, if I wanted to make it look perfectly like that, I could just rotate, maybe rotate this graph. Or just like, so that C and D. So I'll just do a third graph here, where I'll just rotate the vertices and have C and D, instead of being the lower left and upper right, have them be in the upper right and upper left and lower right. So let me just make one more graph here. So just this was moving vertex B. Here's rotating the vertices. So now C is up here. Just changing the labeling. C up here now. Just having C up here where B is, and D down here where A is. And if I do that, and just kind of and then shove B over, shove A over, just rotating the labelings, and make all the same connections. We have A to C, right? A to D. Then B to D, B to D, B to C, and C to B I've got, C to A I've got, C to D, and then I've got D to A, I've got D to B, I've got D to C. I'm just moving the points around. And now you can very easily see these are definitely isomorphic. I mean, they're the same drawing. So now this function, right, the bijection I would set up, right, from say f from the vertex set of graph 1 to the vertex set of graph 2, well, would be the following. I just I'll just draw a picture again, a mapping. You could set it up as a set of ordered pairs and whatnot, as a function. But we're going from 1, 2, 3, 4 over here to A, B, C, D. And then after all this moving points around and making the same exact connections, I can very clearly see that if I map 1 to C, if I map 2 to B, if I map 3 to D, and if I map 4 to A, you get the exact same connections. All right. So if I were to relabel, right, if I were to relabel D as 3, if I were to relabel A as 4, relabel B as 2, and relabel C as 1, then the edge sets, these would be the exact same graph. They'd have the same vertex set now, 1, 2, 3, 4, and they'd have all the same edges, all the same connections. All right, now this reforming the graph, just moving points around, not always easy to see. All right, not always easy to see, especially when there are many, many more points, vertices, and many, many more edges. I mean, this could get pretty crazy. All right. But for right now, most of our examples are going to be reasonably small. So maybe you can see one of these reformations of the graph. All right, and another thing I'm going to point out too, right? Notice that this is kind of broke. This is like triangles and a square around it, two triangles forming a square. Again, this in isomorphic graphs. So these are isomorphic, I'll say, right? These graphs are isomorphic. They have the same form. In isomorphic graphs, every structure is preserved. A triangle up here, right? 3 edges up here that form a triangle should correspond to 3 edges that form a triangle in the other graph. These 4 edges form a square or a 4 cycle. So those same 4 edges, right, should correspond to 4 edges down here that also form a 4 cycle or form a 4-sided figure or a square or whatever. But they should, the structure should be preserved. All right. And that's what they get into after all this. Right, talking about preserving things. What gets preserved under an isomorphism? All right. So in order to verify that a graph G is isomorphic to a graph G prime, it is enough, right? It is sufficient to find this isomorphism from G to G prime, right? This bijection that preserves all the edges, right? Checking that a function from V to V prime, or the vertex S, is an isomorphism can be done efficiently. However, what if G is not isomorphic to G prime? How do we determine that? That might be more difficult. Is there a way to verify that an isomorphism does not exist? In general, there is no efficient algorithm known that can provably determine whether 2 graphs are isomorphic or not. However, in many situations, 2 non-isomorphic graphs have properties that make it easy to either verify that they are not, isomorphic. All right, so say consider an isomorphism F, right, a bijection from the vertex set of graph G to the vertex set of G prime that preserves the edges. The bijection F, right, maps vertex V in G to a vertex F of V in G prime. By the definition of an isomorphism, a vertex W is a neighbor of V and G if and only if f of W is a neighbor of f of V and G prime, right? That's just meaning that, if something's an edge in the first graph, it's going to correspond to an edge in the second graph with the new labeling. Therefore, the degree of a vertex in the first graph must be the same as the degree of what you map it to in the second graph. So look at this, right? Back on my paper here, right? So what they're saying is, in my this is my bijection here that preserves all the edges, right? So 1 maps to C. What's the degree of 1? Right, it's 3. Look, what's the degree of C? It's 3. 2 map to B. What's the degree of 2? In this graph, it's 2. What's the degree of B? Also 2. 3 maps to D. What's the degree of 3 in this graph? It's 3. What's the degree of D in this graph? It's also 3. And 4 maps to A. Degree of 4 is 2. Degree of A is 2. So degrees get preserved under isomorphism. Right? So if a graph G is isomorphic to a graph G prime, then G has a vertex of degree D if and only if G prime has a vertex of degree D as well, right, of the same degree. A property is said to be preserved under isomorphism if, whenever 2 graphs are isomorphic, one graph has the property if and only if the other graph also has that same property, right? All right, so this theorem states that, again, vertex degree is preserved under isomorphism, right, which was already stated. And then they have a very easy proof here, and I'll let you read that. So if so if two graphs are isomorphic, then the vertices have to map to other vertices with the same degree. So that means if you have 2 graphs and there's a vertex in one graph that has a degree that no vertex in the other graph has, they have to not be isomorphic then. You cannot find a map, you can't find a bijection between the vertices that would preserve all the edges. For example here. So look at this graph and this graph. Now they both have 5 vertices, and they both have 1, 2, 3, 4, 5. They both have 6. Right? They both have 6 edges. Like I said before, though, just because 2 graphs have the same number of vertices and the same number of edges, that doesn't mean they're going to be isomorphic. All right? Now, so far, we've only seen examples of isomorphic graphs, but here's 2 non-isomorphic graphs. So same number of vertices, same number of edges, but look, this graph on the right. Look at this vertex here that my cursor's flying over. This vertex has a degree of 1. There's only one neighbor, one edge coming off of it. If these were truly isomorphic, then this graph should also have a vertex of degree 1, because degree is preserved under isomorphism. But look at all these vertices. That is degree 2, degree 3, degree 2, degree 3, degree 2. This graph has no vertex of degree 1. This graph has a vertex of degree 1. So they cannot be isomorphic. You will never be able to relabel these vertices so that you get the exact same structure as this graph over here. That's not going to happen. All right. Again, that's because degrees are preserved under isomorphism. All right. So look here. So each question, shows a pair of graphs which are not isomorphic. state why they're not. All right, and then they give you some options. Well, look, they have the same number of vertices, right? They both have 6 vertices. This has 1, 2, 3, 4, 5, 6, 7 edges. This has 1, 2, 3, 4, 5, 6. This only has 6 edges. Remember, if two graphs are isomorphic, they have to have the same number of vertices and same number of edges, because all the edges in one graph have to correspond to an edge in the other graph. So these have different numbers of edges, right? That's why they're not isomorphic. All right, so now this graph, 4 vertices, 5 vertices. Again, these graphs can't be isomorphic. There's no way to set up a bijection between 4 vertices and 5 vertices. Right? Now here, 6 vertices. Okay, so far so good. 3, 4, 5, 6, 8 edges. Right? There's 4 here, and then 2, 4, 8 edges here. 1, 2, 3, 4, 5, 6, 7, 8 edges here. So they have the same number of vertices. They have the same number of edges, but they're telling us they're not isomorphic. So it must have something to do with this degree property, right? The degree preservation. Well, let's see. Over here, look at this vertex here. Has degree 1, 2, 3, 4. Same with this vertex. This vertex has 1, 2, 3, 4. Do any of these vertices have degree 4? Well, that's 2, 3, 3, 3, 3, and 2. So this has a couple vertices with degree 4. And remember, if they're isomorphic, they should have the same number of vertices with the same degree. This graph doesn't have any vertices of degree 4. So these degree 4 vertices are messing it up. Right? These graphs are not isomorphic. They don't have the same structure. All right, so then they extend this a little bit further, talking about the degree sequence of a graph. And this is just, you just go around labeling the degree of every vertex and then put them in non-increasing order, putting them from highest to lowest. Put those degree numbers in order. This is called the degree sequence of a graph. And as you probably have guessed, if two graphs are isomorphic, then they will have the same degree sequence. Right? Because again, every vertex in one graph will correspond to a vertex in the other graph with the same degree. So you should have the same degrees all the way around. So when I put them in order from greatest to least, it'll be the same numbers in the same order. All right. So for example here, what is the degree sequence of this graph? Let's see, you got a 2, a 3, and a 3, another 3, and a 2 and a 1. Right, if you go for, so you have 3 3s, 2 2s, and a 1 for the 6 vertices. So 3 3s, 2 2s, and a 1. And putting them in non-increasing order from highest to lowest. Okay. And any graph that if there's a graph isomorphic to this, it'll have the same degree sequence. All right. So they're showing you here now. So basically, hopefully you remember way back in the logic chapter of our Xi books, we had conditional statements. So what we're saying here is the following. We're saying if two graphs are isomorphic, then they will have the same degree sequence. So remember, this is a conditional statement, right? If P, if this statement, which I'll call P, then this statement, which I'll call Q, right? If P, then Q. Now, if you recall back from a long time ago, right, proofs and stuff, logic, this is logically equivalent to the following. Remember, it's logically equivalent to, or just this, the 3 equal sign, the contrapositive. Remember, every if P then Q was logically equivalent to the contrapositive, which would be if, not Q, then not P. So, another so if two graphs are isomorphic, then they're going to have the same degree sequence. The contrapositive of this is if they don't have the same degree sequence, then they're not isomorphic. All right, so that's true. But many people often mess up with this. Remember, this this is not logically equivalent to the following, right? So not logically equivalent to the converse, right? Remember, the converse of a statement is the following. If Q, then P. Right? So this is not true all the time. Right? This is a true statement. This is not I'll say not necessarily true. Right? It could be true in some cases. It could be false in other cases. So if two graphs have the same degree sequence, then they're isomorphic. That's not true. Right. Some graphs have the same degree sequence, but are not isomorphic. We'll see that coming up. So just be careful. Just be careful. So here they give us an example where here's a graph in blue, here's a graph in red. They got the same number of vertices, the same number of edges, so they might be isomorphic. But notice they do not have the same degree sequence. All right, and if they don't have the same degree sequence, this was the contrapositive, right, the one that was equivalent, that was true. If they don't have the same degree sequence, then they're not isomorphic. Right? You cannot find a bijection between the vertices that will preserve all the edges. All right, but then they get into, all right, well, what if is every pair of graphs with the same degree sequence isomorphic? No. So just because two graphs have the same degree sequence, right? So like these two here, both of these have 8 vertices, right? Both of these have 8 vertices, and every single vertex in both of these graphs have degree 3. So the degree sequence would be, and they also have 8 edges. No, 10 edges, don't they? 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8. So they have 12 edges. But there's 8, but again, each of the 8 vertices has degree 3. So the degree sequence for both of these is 8 threes. Right? So you're like, hey, they have the same degree sequence, so they must be isomorphic. No way. No. Just because graphs have the same degree sequence, that does not mean they are isomorphic. All right, remember the thing I was mentioning earlier about, cycles in a graph, or shapes you can form in a graph, connections. So remember back to this here. See, in these two graphs from an earlier example, right? These are isomorphic, and I had the bijection here. So you see vertices 1, 2, and 3. When you look at all the edges they correspond to in connection to each other, they form a 3 cycle, right? Or a triangle. A cycle with 3 edges, a closed curve with forming a shape. If you look at the corresponding vertices, right, 1 corresponds to C, 2 to B, 3 to D, and then their corresponding edges, they form another 3 cycle. So that's another thing, and this is actually discussed in an exercise, one of the additional exercises. That's another thing that's preserved under isomorphism. The number of 3 cycles will be the same. The number of 4 cycles will also be the same. 1, 2, 3, and 4. If you look at this connection of edges, form a 4 cycle, right? A little 4-sided shape. Their corresponding edges down here, right? This edge corresponds to this edge to this edge, this edge to this edge, this edge to this edge, forms another 4 cycle. So if you look at how the corresponding, in a bijection, in one of these isomorphisms, if you look at how the corresponding edges match up, if they form a cycle in one graph, they're going to form the same kind of cycle in the other graph. So cycles are also preserved under isomorphism. So look at these 2 graphs here. Look at the left graph. Look at, say, where my cursor is. Look at these three vertices here. So you see these edges form a triangle, a 3 cycle. So if there were an isomorphic graph to this graph, the vertices that these 3 map to, the edges between them would also form a 3 cycle, would also form a triangle. But look at this graph over here. Do you see any triangles in this graph? I don't. So this 3 cycle, right, doesn't map to a corresponding 3 cycle over here. Look in the middle. Look at these 6 vertices in the middle. See how they form like a 6 cycle? A hexagon. So if I was looking at an isomorphic graph, the vertices that these all map to, their corresponding edges should also form a 6 cycle or some sort of hexagon. Do you see any 6 cycle here? I mean, I see a bunch of 4 cycles. Right? There's 4 cycle there, 4 cycle there, 4 cycle there. I guess you could go 1, 2, 3, 4, 5. I guess you could do a 6 cycle. All right, so maybe there is a 6 cycle, but look at this 6 cycle is kind of cut off by an edge here. I don't see any cutting edges through this. Really, it's the 3 cycles that give it away. There's no set of 3 vertices over here where I can start at one, go to the other one, go to the other one, then come back to the beginning. There's nothing like that. There's something like that in the left graph, but nothing like that in the right graph. So they're not isomorphic. They don't have the same structure. So be careful. All right, one more time. Just because 2 graphs have the same degree sequence, that doesn't mean they're isomorphic. All right, so down here mentions that 2 of the graphs pictured below are isomorphic. The 3rd graph is not isomorphic to the other 2. Use the degree sequence to determine which of the 3 graphs are not isomorphic to the other 2. All right, so they're telling me that 2 of these are isomorphic. All right, so I'll leave this one to you. So what I'm guessing, based on how they worded this, is that 2 of these are going to have the same degree sequence and one of them's not. And then that one's going to be the one that's definitely not isomorphic to the other 2. All right, so I'll leave these to you. You go through and just list the degree of every vertex in each of these 3 graphs and put them in order from highest to lowest and see which one doesn't match the other 2. All right, and then graph theory. What were in these first 3 sections of this chapter, 13, 1, 2, and 3? We're basically being introduced to a field of mathematics called graph theory. Graph theory is concerned with properties of graphs that are preserved under isomorphism. So we saw, degree is preserved, right? The degree of a vertex to its corresponding vertex, they should be the same. These degree sequences, therefore, should then be preserved. And another thing I mentioned, and like I said, it's in the exercises. I think it's right down here, see? For any k, having a k cycle as a subgraph is preserved. All right. And then I basically explained this to you already, right? There's a 3-cycle subgraph here, but there is no 3-cycle subgraph over here, so they're not isomorphic. They can't be. But yeah, and there's much more. All right, we're just getting into the tip of it. All right, the tip of the iceberg. There are lots of other crazy things that get preserved under isomorphism. Not just these degrees and cycles. All right. But this is the extent of our course here for this section anyway. Properties preserved under isomorphism, right, relate to the structure of graphs. By contrast, properties that are not preserved under isomorphism depend on the labels of the vertices. Right. So again, the way things are labeled initially, you might think, oh, they're not isomorphic. But then if you do some sort of relabeling, you could probably set up a new set of connections, and then the graphs may be isomorphic. Right? So it's some complicated stuff, even though it's just a bunch of dots and lines. Right? So we have seen that the number of vertices, right, the number of edges, and the degree sequence, right, are all preserved under isomorphism. Also those cycles, right, as I mentioned, but it's in the exercises. So here are some properties that are not preserved under isomorphism. Say the lowest numbered vertex has degree 3. That's not always going to happen, right? You could just relabel so that maybe there's another vertex called maybe if the vertex labeled 1 has degree 3 and a vertex labeled 5 has degree 7, and you just relabel it, then all of a sudden the degree 1 vertex, the one labeled 1 has a degree 7. So this is definitely not preserved. Every even number vertex has an odd degree. Again, you can just relabel things. Make one of these even numbered vertex, label some even degree vertex with a number 2 or something. Just relabel, and then you get some even numbered vertex with an even degree. All right, so definitely not preserved under isomorphism. All right, so the following here, which I've already shown to someone, so you see it's already completed, but which graph properties are preserved under isomorphism? Well, if the degree sequence is preserved, remember total degree was just the sum of all the degrees. Well, if every degree is preserved, then the total degree is definitely going to be preserved under isomorphism. The number of vertices whose degree is an even number. Well, absolutely. Again, if the degree sequence is preserved, then the graphs will have the same number of vertices with the same degrees. So the number of vertices whose degree is even will also be preserved. The sum of the degrees of the even numbered vertices. Now this won't be preserved for the reason I set up here. If you just relabel things, so again, say one of the even vertices has an odd degree, you can relabel it so that it's another vertex. You just change another vertex's labeling to be an even number with an even degree, and it'll change the sum of those even numbered vertices. So this is not preserved because things can be relabeled. The number of edges minus the number of vertices, absolutely. Because remember, the number of edges is always the same between two isomorphic graphs. The number of vertices is always the same between two isomorphic graphs, so this subtracted number would always be the same as well. Alright, so that was a long one. It was a little over an hour, but this is some heavy stuff. Okay, determining if two graphs have the same structure. Are they isomorphic? Can I find a bijection from the vertex set of one graph to the vertex set of the other graph that preserves all the same edge relationships, all the same connections. And then you have your additional exercises. Now, fortunately, there's not too many of them. Well, I should say unfortunately. You probably should practice more of this, but I'm hoping there's enough here to where you get a taste for it. I probably assigned all these. Maybe not the last one because I already kind of discussed it. So again, if you want, if I didn't assign all of them, still look at them all, just for more exposure to the material, more practice. You can also check out the solutions if you want. But please, try to work things out, try to figure things out before you look at the solutions. You're not going to learn anything if you just look at the solution, copy it down, and don't try anything. And obviously, if you have any questions, send me a message. I'll get back to you as soon as possible. And I hope this video was a reasonable guide through this section. And thank you very much for watching.